So we'll be explaining FFT, or the fast Fourier transform. So this is a method of multiplying polynomials together that's used in competitive programming. It can be used for other things too, but primarily it's used for multiplying polynomials. So your traditional polynomial is given in the coefficient representation. So that would be ax is equal to some summation from I equals 0 to n, a sub I, x to the I. So you can sort of store and represent this as just a vector a, which is just all the different coefficients, which is how it gets its name. So the thing with this is that whenever you want to compute the sort of product of two polynomials, so ax like times bx or something, that's going to take you, if each of these has n terms in them, or on the order of n terms, this is going to take you O of n squared operations, because if you write this out, you're going to get a0 x to the 0 plus a1 x to the 1 plus an x to the n, and then b0 x to the 0 plus b1 x to the 1 plus b n x to the n. So for every single one of these terms, it's going to need to be multiplied by every single term in the other sequence. So if there's n things here, I need to do n multiplications for each one of these n items. So that's just a simple like double for loop going to n each time. That's going to give you O of n squared operations. So if you had a competitive programming problem where you had to multiply two polynomials and they were quite large, you had a very short time limit, the standard method of multiplying polynomials is too slow. But there is a way to sort of get around this sort of n squared, sort of seeming, it seems like that would be the best way to do it, but there's actually a better way to do it, and that is the whole point of the fast Fourier transform. So there's another way of representing polynomials. This is called the point value representation. So for a set of points, we're going to call this just x bar, let's call it that, and then you just go x0, x1, all the way to xn. You will have x0 and then a of x0. And you're just going to keep on doing this for each different point inside of the x0 vector. And the sort of benefit of this is that you can do a lot of things that's quicker with this. But you might be sort of wondering that this might not be a good representation, because how do I know that this is like the only way that I can represent A? Like, how do I know that there isn't some other polynomial B which has a different coefficient representation than A, but it has the same point value thing? Like, it's unintuitive that this would be a good way to represent polynomials. But there's actually a way that you can sort of represent that, is that there's this thing called a Vandermonde matrix, which I won't go into much detail about. Just know that it's invertible, and that V of, let's just call it V of n times x bar is going to equal this matrix A of x0, A of x1, all the way down to A of xn. And then the nice thing about this matrix is that this is an invertible matrix. And we're going to call each of these points, we're going to call those just y. So like y0, y1, all the way down to yn. And we'll just represent that as y bar. So because this is invertible, I can sort of rewrite this as Vn times x is equal to y bar, but then I can multiply both sides by the inverse of this Vandermonde matrix. And when I do that, these two are going to cancel out, and I'll be left with x bar. Oh, it's actually not x bar, it is a bar. But yeah, so the Vandermonde matrix times each of the coefficients in A is equal to each of these values. This matrix is invertible, so I can sort of just get rid of it on that side and just be left with each of the values is equal to the answers times this inverted matrix. So there's a unique inverse of each matrix, which means that there is only one way that I can sort of get this answer. There's a unique point value representation for some set of points for each different polynomial. So there's a one-to-one correspondence between, or there is a one-to-one correspondence between point value things and then polynomials. This is very nice because then this is actually a good way to represent polynomials, because I can't get two things mapping to the same thing, or one thing that maps to two different things, which would be very bad. Okay. But now that we know that there's a different way to represent polynomials like this, we can sort of look at how well we can multiply things, how we can add things with this new representation. So we know that if we got two polynomials, a of x, and we want to multiply that by b of x, that's going to give us some new polynomial of c of x, right? So the thing though is, with this point value representation, if a of xi, if I look at a of xi times b of xi, that then is also equal to c of xi. But the thing is, with this point value representation, I already know what a of x and b of xi are. So that's like y of I for a, and then this is b yi. So this is just like the y value from its point value representation. So that just takes O of one time. And then I can do this for each one of the different xi values, and then I can just do that. There are n xi values, so that's going to be O of n times O of 1. So I can just, instead of having to go through and multiply every single thing, which is going to take n operations per n thing, now it's just going to be O of 1, because you've already computed the sort of value at a point. So because I've already done that work beforehand, if I just somehow got each one of these representations, it will take me just O of n time to multiply them, which is much better than the actual representation over there. So we can sort of look at this as like a bit of a diagram, where if you just have just like the coefficient representations, I can then multiply them to get the sort of answer. So that's like multiplication. I can do that in O of n squared time. I can do that directly. Or I can go to the point value domain. I can do that in O of n time, actually, because all I need to do is evaluate a polynomial n times. Actually, wait, that's not O of n time. That is O of n squared time. So that's a bit expensive, because I need to evaluate a polynomial. That's going to take O of n steps, because I need to evaluate it at each one of these different coefficients. And then I need to do that for each of the n points that I need to have. So that's O of n times O of n. So that's O of n squared. The thing that's nice, though, is that if I have the point value things, I can then find the multiplied point value bit. I can do that in O of n time. And then I can sort of get back to the beginning over here. I can do that in O of n squared time, because multiplying this matrix, this is a n by n matrix, that's going to be at least O of n squared time. So we could just immediately go from here to there, and that would take n squared time, or we could go around this other path that's going to be n squared plus n squared, which is going to be still n squared time. But if there was a faster way to go across this, to sort of like get rid of these n squared terms, then we could multiply polynomials faster than n squared time. So this sort of way of bypassing these n squared, these sort of naive point value transformations, the act of surpassing them is the fast Fourier transform. So the way that you do that is, instead of evaluating these at the sort of arbitrary xi locations, you're going to evaluate them at these things called the roots of unity, the complex roots of unity. And by doing that, you can make a divide and conquer algorithm, which will sort of get around that by doing an algorithm that takes n log n time. So to do a sort of little quick explanation of the roots of unity, we're just going to sort of just go for it. Okay, so this is the sort of base root of unity, which is just e to the 2 pi I over n. And then each one of the roots of unity for the principal root of unity, wn, is just a power of it. So it's going to be wn to the power of 0, wn to the power of 1, w omega n to the power of 2, all the way up to omega n, it's not w, it's actually omega, to the power of n. And this is actually the same as that. So one thing to know about this is e to the I theta is equal to cosine of theta plus I sine of theta. The reason why that is important is because then you can look at this at the complex plane. So the very first root is going to be just 1 because it's some number, this guy, to the power of 0. That's the primary root, 0, wn 0. So this is going to be the complex plane, so that's just real numbers right there and imaginary numbers on the other axis. So the 0th root for any one is just going to be 1. So it's going to be viewed as this vector right there. And then as we go across this, we're going to increase the power. So I'm going to be increasing this angle. So the first root is going to be some angle up from there. Second root is going to be some angle up from there. And it's going to keep on going throughout this circle. And eventually it's going to end up back right at the beginning. And it's going to end up at the beginning right at the nth root, which is just how the complex roots work. There's also some nice properties, which is that omega of n over 2, n, that is equal to -1. That's just the Euler identity. If you plug in n over 2 to that power right there, you will just get e to the pi I, which is -1. And then omega of dn dk is equal to omega of k n. You can again get that because if you put in dn right there and put a power of dn right there, the power of d and dividing by a power of d will cancel out, and you'll be left with this. So that's called the cancellation identity. So the thing that's nice about this is that if we have some polynomial in a coefficient representation, say a0, x0, all the way up to an, xn, I can then sort of make two separate polynomials. a0 of x, which is going to be all of the even coefficients, all the even terms, except we're going to sort of just ignore the original powers on them. So it goes from x to the 0, x to the 1, x to the 2. So you can sort of see that each one of these terms is actually half of what it used to be. We're also going to say that n is a power of 2. And we can assure that this is always true because if your polynomial is less than the power of 2, you can just add a bunch of terms at the end that are just zeros. So it'd be like plus 0 x to the n plus 1 plus 0 x to the n plus 2. And you can just sort of get away with that just because it doesn't actually change the values of the polynomial. You'll actually also have to use this trick when you're multiplying polynomials because, like, let's say if you have a degree n polynomial, so if a is a degree n and b is also a degree n, then c, the sort of product of these two, is going to be a degree of 2n, maybe plus 1. Yeah, no, it'll just be 2n. Because the biggest power in this times the biggest power in this will be twice the original power, so it'll be c of 2n. So when you want to get the point value representation of c, you need to make sure that you evaluate it at 2n points, because you need to have it at the degree number of points. So you also get around that just by adding extra zeros to the front of it, because that also doesn't change the value. So you just want to make sure that you resize this to be you just need to add enough zeros so that you have enough terms in it to make this actually make sense. So that's just, you want to double it and then put that up to the biggest power of 2 above the doubled answer. So it's going to be at least 2n. It will be as big as like 4n. So yeah, just remember that. Just make sure it's a power of 2 also. But then after you do that, you're going to have all these different terms. These are all the even terms. So then you're also going to have all of the odd terms. And it's going to be the same sort of weird thing where we just sort of like ignore the original powers on x. So you can sort of see a pattern actually forming, which is that all of these powers are half of what they actually should be, because they're all the even terms and they just got halved. Then all of these terms are half what they should be, but they're like halved and floored. So we can sort of rewrite a of x as these polynomials So all that changed with a superscript 0 is that all the powers are halved, so we can just double them by having this squared here. Because if I plug in squared, that's going to be squared times 0, 0, squared times 1 is 2, which is the original power. And the same thing holds true for every other one. And then these got halved and floored, so I'm going to need to add one and also double them. So doubling them is just what we did a second ago. But then adding 1, you're going to have to multiply by x. So that does the same thing as shifting these all to the right, which is good. So then we said we're going to evaluate these at the complex roots of unity, which is why we talked about them up here. So let's sort of assume that we've already done this. We're going to be doing a divide and conquer algorithm, so we're just going to sort of assume that we know what these are evaluated at their complex roots of unity. So remember that these roots of unity are going to be at n over 2, and then so that this one is going to be at just n. So I'm going to want to evaluate a at the complex roots of unity n, k, just for each one of the k's. But then for each one of these, for a0 and a1, I've evaluated them at k, but at n over 2. So with some clever writing, we can actually see that these are kind of the same thing. So I can write this as, I want to evaluate that at kn. I can rewrite this, but I actually want to evaluate it at kn squared, because I'm squaring it right there. So I'm going to square it right there. So I can write that as 2 times n over 2. This is just the same thing as n, k, and then it's squared. So that's the same thing as 2k, because this is just a power. It's not a superscript. 2k, 2n over 2, and then with that cancellation lemma, we get omega of k, n over 2 is what we want to evaluate it at, which is actually the exact same thing we evaluated right here. The thing is, though, that we only evaluated n over 2 of them. So we have to think about, what do we do for the other n over 2? So this works for the first n over 2 k's, k values, but the second n over 2 ones could be different. But then we need to remember that this thing, that omega n over 2 is equal to negative 1. So if we look at k plus n over 2, n, this is just a power, so I can just sort of rewrite them as products of each other. And then that's just equal to negative omega kn, which is what we just wanted to evaluate them at. Then remember that this is squared, so when you square this, you get the exact thing that you were looking for a second ago. The negative 1 just gets erased because it's squared. But then the only thing you need to remember about is that this x is not squared. So you need to remember that this is going to be the opposite of what it was in the first part. So then now if we look at the Clrs algorithm for FFT, you will actually find that it's just pretty much exactly that, except for their base case, they said if n's length is 1, which means if you're looking at a degree 1 polynomial, you can just return the coefficient, and that's because no matter where you evaluate a constant number, it's just going to be the number, which is a. Then they set up their sort of omegas, and they get the a0, a1, the even terms and the odd terms. They find out what the actual values are, and then from k from 0 up to n over 2 minus 1, they use the exact same thing that they found in the previous one, then omega times the exact same they found in the previous one, and then for the one where you shift it up by n over 2, this one stays positive because it's a squared negative number. This one needs to become negative because omega of n over 2, omega of n to the power of n over 2 is negative 1. And then that's just it. And then you get y, and it's correct. So that is why FFT actually gives you the fast Fourier transform of two polynomials. Then when you want to actually multiply the two polynomials, all you need to do is, I can show you my code on the screen. When you multiply them, all you need to do is actually just go through and multiply the actual values. So I made a and b equal to their point value representations, and then you just need to multiply the actual values that you found. And then when you want to get the reverse, the inverse, when you want to go from the actual, I'm going to look at the diagram again. when you want to go from the point value representation back to the coefficient representation, all you need to do is take the conjugate of each of these values. So once you found your actual complex numbered point value representation, all you need to do is take the conjugate of that, run it through FFT again, and then just use the real part. Then you can also notice that I'm using the complex library inside of C++. You also want to have a very accurate representation for pi. The integers will get very big because you'll find it's sort of like Pascal's triangle almost, but you'll find that some numbers get very big because there are many different ways to make n over the power for n over 2. And then yeah. But for the complex long double, we talked about how e to the I theta is equal to cosine of theta plus I sine theta. Well, that really is just telling you that if you want to look at this as a polar value, all of these lengths are going to be 1 because omega is always going to be e to some power, so the radius is going to be 1. There's like an invisible r, so it would be r cosine theta plus r I sine theta, and the r will be 1 on both of those because you don't actually have an r. And then the actual angle is just the power that e is going to, because it's I theta, so the 2 pi divided by n is your theta, which is 2 pi divided by n, a dot size, yeah. So that's just how you implement FFT. There's a little bit of tricks here and there, and yeah. When you're actually initializing it, again, you're going to want to make sure that you make the vectors big enough. If you're multiplying them, you're going to want to make sure that the vectors are twice as big as what you think would be big enough. Because you need to make it the biggest power of 2, and then you need to make it twice that so that you actually have enough points to create your new coefficient list. And that's it, yeah. Oh, one very, very, very last thing is that these sort of functions, if you make them return things, it can make them a lot slower than they actually are. So if you make things void and make everything pass by reference, you can speed up your code quite a lot, and you probably will need that because if your polynomials are big enough that you need FFT, they're probably also big enough that you need to optimize your FFT. Okay, so then that's everything. Thank you for watching, and I hope you learned how FFT works. Oh, my name is also Reginald Frank at Texas A&M, doing this for 489. Alright, I'm pretty sure that's all I need to do. Okay, bye-bye.